we will introduce the two sets problem and then an algorithm for solving this problem. Suppose that f is a formula with Boolean variables. So here we have an example. This f is x or y, and then or the result of not y and x, and we take the whole expression and the negation of x. So by plugging in values for x and y to be true or false, then in that case, f will now have a value of true or false. The SAT problem, SAT problem, asks if we can assign true-false value to the variables so that this big F will become true. Now in this example, it is yes. It is possible that we can assign true-false value to the variables to make the formula F true. So here is one example. This is F when x is f and y is t. So let's take a look. So first of all, when x is f, then negation of x here is t. So and t, so we can ignore it later. And now when y is true, then this part is true because y is already true. True or anything is true. So this part is true. And for this part, we don't need to care about this one because it is already true. True or anything is true. So the whole expression up to this point is true, and because negation of x is already true, we have seen that true and true is true. Okay, so in that case, we see that the formula f can be made to be true, and in that case, we say f is satisfiable, can be satisfied. Okay, now let us modify the problem a little bit into the so-called k-set problem. In the k-set problem, we will restrict the formula f to be of a special form. So first of all, we define what is meant by a clause. A clause is a disjunction of these variables or the negation of the variables. So disjunction means or together. So x or y is a clause, not y or z or w is a clause. So we have variables or literals, we call it, because it's the negation form of a variable. Another literal, another literal. So when they are all together, they form a clause. Okay, and then a k clause is a clause with k literals. So here, x or y, we have one literal, another literal, so we call it a two clause. And this one, this is a three clause. And now what is a k-set problem? So the input formula f in a k-set problem is restricted to be a conjunction of k clauses. So what does that mean? So if we are talking about a two-set problem, the formula must look like there is a two clause here, there is another two clause here, there is another two clause here, but then the whole formula is the conjunction, the and of these clauses. Okay, so we have a bunch of two clauses and together. And for the input of a three-set problem, then it is the conjunction of three clauses. So this is a three clause, this is another three clause, we AND them together. So this is the input of a three set. Okay, now, so the focus now here is I have a two sets problem. So I'm given a formula that is of the two set format. So can we determine whether there exists a certain assignment of the variables so that the formula becomes true? So this is the two sets problem. Now two sets problem can actually be solved in linear time. On the other hand, three sets problem, just changing the clauses format into three clauses instead of two clauses, then the three sets problem suddenly becomes an NP complete problem, which means that at this moment, no polynomial time algorithm is known to solve this problem. So here, two sets can be solved in linear time, but three sets, no polynomial time. So far, we don't know any n square algorithm, n cube algorithm for solving three sets. And what happens next is here in this lecture here is we are going to design a randomized algorithm for two sets. But you may ask, two sets can already be solved in linear time, so why do we bother to solve this by using a randomized algorithm, which may be wrong in some of the cases? The reason is that this randomized algorithm for two sets may not be useful, but then it can be adapted for three sets, which will be the focus for the next lecture. So let's see how we can solve two sets by using randomization. Okay, so this is the algorithm. So we have an input formula f. Okay, so what we are going to do here is we pick a random assignment, let's call it a, for the variables. So let's say the formula has variables x, y, z. Maybe we pick x to be true, y to be false, and z to be false, just any assignment. And then we are going to repeat the following loop t times. This t will be fixed later. Okay, so what do we do? Okay, so we have a current assignment A, so we check whether the formula is already true under the assignment A. If it is not true, what we are going to do here is that if it is not true, that means that for a certain clause in this f, under the current assignment, it is still false. Because otherwise, if all of the clauses are true, then f will be true. Okay? So there must be some clause which is currently false. So we pick randomly any one of the clause that is false. And then within the clause C that we have selected, C has two literals, or it is related to two variables. We know that the current assignment of these variables does not make the clause C to be true. So what we are going to do here is that we know that if there exists a correct assignment that makes f to be true, then one of these variables, or both of them, are currently not the same as the current assignment. So we try to make some progress. So what we are going to do here is we guess which variable are assigned incorrectly. So we pick a random variable. We pick a variable randomly from this clause C and flip the value. So this is the case where f is not true. On the other hand, if f is true using or under the current assignment A, so we can exit the loop directly. So what we are going to do here is that as long as f is not true, we are going to pick a random clause and flip a variable. We do this for t times. After that, whenever we have exited the loop, either due to this part or after running it for t times, then we will check whether f is true for the current assignment. If so, we will return yes. Otherwise, we will return no. So let's see an example run for this algorithm. So let's say the current formula f is equal to this one, and we pick a random assignment TTF for x, y, and z. So in that case, we will see that for the middle clause, negation of x is false, and z is also false. So in that case, this is a false clause. So let's pick this one, and then flip one of the variables. So let's pick a variable. This time, let's say we flip x. Okay. So after flipping the variable, the assignment TTF will now become FTF. Now when we have FTF, after careful checking, we will see that each of the clause is now true. So true and true and true will make F true. So in that case, we will exit the loop and then return yes. And then for another case, this is another example. Suppose that we have the same formula F, but this time the initial assignment is FFF. And then we will see that under this assignment, one of the clause here, x or y, is false. So what we are going to do, so we pick a variable randomly from it, x or y randomly. So let's say x, and flip the value. After flipping the value, the assignment changes from FFF into TFF. So here we will see that after changing this, the formula F is still not true. So we will repeat the process, pick a false clause and flip a variable, and so on and so forth. So we will either do so repeatedly for T steps, or when F suddenly is satisfied, then we will exit the loop. Okay, so this is another run. Okay, now let us analyze the performance of this two-set algorithm. So first of all, we see that if the formula F can never be satisfied, so which means that no assignment could make F true, then the algorithm always return no. The reason is that, we are always testing an assignment for F, and then none of them could ever make F to be true. So in the end, we will run this algorithm, run the loop for T times, and then finally we still fail to find any assignment that makes F true, so we will always return no. And in such a case, the algorithm will be correct because it correctly tells us that F is not satisfiable. On the other hand, our algorithm may make mistake, and it makes mistake only when what? When okay, so there is a typo. So it makes mistake when F is really satisfiable. So we can actually satisfy F. But then our algorithm fails to find an assignment to make F true. So we will wrongly decide F is something that is not satisfiable. So we want to analyze what is the chance of this error rate. Okay, so here, if you revisit our algorithm, the idea here is that the algorithm tries to search for a certain A star that makes F true. So we will assume that there is a certain A star that makes F true, and see after each modification of the assignment, can we ever get into this A star? So when F is not true, let us use A to represent the current assignment of the variables. We let C to be the selected clause that is false. We let XY to be the variables that appear in C. And then, as we have mentioned before, this A star and A, they will assign values, true or false values, differently for X and Y. Sometimes one of them will be different, sometimes both of them will be different. Okay, so they are just different if you look at XY together. Okay, so here, X or Y or both are assigned differently in A and in A star. So when we pick X or Y randomly to flip, so at least 50% of the chance A will look closer to A star. So there's more of the values that is assigned to be matching. So let us model this as a stochastic process where each state denotes how many variables of A and A star agree. So let's use the next page. Okay. So the maximum number of matches is n, in which case A and A star are the same, and the minimum number of matches is 0, where A and A star are completely different for each of the assigned value for each of the variable. And then we will see that, so there are states like 0, 1, 2, 3, and so on and so forth. And then if we are at state 0, any time that we pick a variable, it must go to state 1. Because completely different. When we pick any variable and flip it, then it must be one more matching. But on the other hand, if we are at a middle state, let's say state 2, then we can go to state 3 if we guess correctly which variable to flip. And sometimes we don't need to guess. It is because when both of the variables are assigned differently in A and A star here. So in that case, the probability that we move from this state 2 to state 3 could sometimes be equal to 0.5, could sometimes be equal to 1. So in that case, I'm using greater than or equal to 0.5 to represent this action. So when we look at this, this is somehow a high-level model to describe what is going on when we run our algorithm. But our focus here is we are going to analyze Markov chain, but this is not a Markov chain. Yeah, why is it not a Markov chain? The reason here is that for Markov chain, the probability that we move from any state to any other state is always fixed. So here in our actual algorithm, sometimes this is 0.5, sometimes this is 1. But so this is not a Markov chain. In Markov chain, this has to be a fixed probability. So in that case, we get a related Markov chain as follows. So instead of having uncertainty here on the edges here, we make it to be specific without any uncertainty. So it is 0.5, 0.5, 0.5, and so on and so forth. But if you compare the two process, so our goal is always to reach this state n. This is the case where we can exit the loop, or this is a state that we can find a satisfying assignment. So we want to reach this n. But if you compare this process, this is the actual algorithm running, and this is the related Markov chain, we will see that for this one, it has more chance to move forward than move backward. But this one, it has equal chance to move forward and backward for the intermediate states. So in that sense, if we want to reach state n, then the previous case, the algorithm, is easier, while this Markov chain is harder. So formally, so let us use X to describe the stochastic process in the algorithm in the first model, and Y be the stochastic process, that is the related Markov chain that we have just seen. We saw that it is much easier for the first one to reach state n than the second one. So we have the expected time or expected number of steps for the first stochastic process x to reach n starting at x0 for some x0 is less than or equal to the expected time for y to reach n starting at y0, where we assume that x0 and y0 are corresponding to the same assignment, the same initial assignment. So we will see that this one reaching in the model is easier. So if somehow we can have the expected value of this one, then it gives us an upper bound of the expected value of this one. Okay. So the next part here is we want to do the bound for expected time for y to reach n starting at y0 for any value of y0. We want to show that this expected value is less than or equal to n squared. If this is the case, then for any value of x0, the expected time for x to reach n starting at x0 will be less than or equal to n squared. So no matter where we begin with, the time to reach n in the randomized algorithm is less than or equal to n squared in the expected sense. Now, if this is true, then the probability that x cannot reach n in 2n squared steps will be less than or equal to 1 over 2. This is by Markov inequality. We can reach the expected time to reach is n squared. So if I give you 2n squared and you still cannot reach, then it is less than or equal to 1 over 2. If I give you kn squared step, then it is less than or equal to 1 over k. So this is a simple application of the Markov inequality. And now, if we make further, so this time, if we are given 2n squared multiplied by log n steps, then in that case, we cannot reach n. The chance will be less than or equal to 1 over n. So how suddenly we can do something like this? It is because when we are given 2n squared times log n step, we can partition them into log n groups of 2n squared step. So the chance that we cannot reach n using these many number of steps, it is the chance that we cannot reach it using the first 2n squared steps, and also the chance that we cannot reach it using the second 2n squared steps, and so on and so forth. So this will fail. So will fail with a chance of 1 over 2 to the power log of n. So this will only fail with the chance of 1 over n. So this is how we can obtain. So in that sense, this is the t that we are going to set in our algorithm. So if we allow the process to run for 2n squared times log n steps, then with high probability, if the formula is satisfiable, we should be able to reach state n. And if we do not reach state n, then with high probability, then the original formula f is not satisfiable. So in other words, the two-set algorithm returns no when f is not satisfiable. This is what we have known already. But on the other hand, if we set t to be 2n squared log n, the algorithm returns yes and finds a satisfying assignment with high probability. Okay, now, so we are nearly done. The only thing that we have not shown here is that this is a claim so far. We are claiming that the expected time for the Markov chain to reach state n starting at any state is less than or equal to n squared. So let us proceed with the proof of this one. Okay. So here we use h of j to represent the number of steps to reach n starting at j. So we are focusing on the Markov chain. So here, all of the things here are talking about the Markov chain. So we have h of 0 is equal to 1 plus h of 1. Yeah, h of 0 means we are starting at state 0. So h of 0 is you always use one step to move to state 1. And then at state 1, we use certain number of steps to reach n. So by linearity of expectation, expected of the case where we start at 0 is equal to 1 plus the expected of the case that we start at 1. So it's 1 plus h of 1. On the other hand, if we are already at state n, then we don't need to move any further. So h of n is equal to 0. And for the intermediate cases, h of j will be equal to, we always use one step to either move forward or move backward. And half of the chance we move backward, so we will further need h of j minus 1 steps to move to state n. On the other hand, with half of the chance, we are moving to state j plus 1, so we will then need h of j plus 1 to move on. So we will see that there are n plus 1 inequalities here, and then n plus 1 unknowns here. So we are able to solve the formula here. And the textbook tells us that, okay, we can actually solve it precisely for h of j to be equal to n squared minus j squared. And then you can actually verify it by yourself by using induction. You can just plug it in and verify whether this is a correct value. And because of this, so we have h of j less than or equal to n squared. So this is showing the claim, right? So that's all for the second part of this lecture.